Hi, I'm Mark Barsamian. In this video, I'll be discussing using marginal quantities to approximate change in quantities. This material is from the book, section 2.7, Marginal Analysis. More specifically, the first 5 pages of that section, examples 1, 2, and 3. The corresponding homework is homework 36, using marginal quantities to estimate change in quantities. It's actually just these two problems, numbers 33 and 43 from section 2.7. In the video for homework 34, we discussed the idea of exact change in a quantity. We discussed the idea of a company manufacturing some item with the cost of producing a batch of X of the items being given by a cost function, C parentheses X. Now suppose that X subscript 0 is a particular value of the variable X. So for instance, X subscript 0 could just be the number 50. And suppose that the company increases the number of items made from that number, X subscript 0, to a new number of items, X subscript 0 plus 1. The question is, what will be the resulting change in cost? Well, the answer to that is the change in cost is denoted by this delta C, and it's computed by just finding the difference. C parentheses x0 plus 1 minus C parentheses x0. So that's the exact change in cost. The book sometimes calls this the exact cost of this item, the x0 plus 1 superscript st item. Now, the exact change in quantity would be how much the quantity changed. That would be denoted by delta x, and that would be this quantity, which is just 1. We changed from a quantity of x subscript 0 to a quantity of x subscript 0 plus 1, so the quantity just changed by the number 1. So, for instance, if the quantity changed from 50 to 51, that would mean that x0, x subscript 0 would be 50, and x subscript 0 plus 1 would be 50 plus 1, that would be 51. And the exact change in cost would be this. Delta C equals capital C parentheses 51 minus capital C parentheses 50. In the book would call this the exact cost of producing the 51st item. These quantities could be illustrated on a graph of a cost function as shown. In this graph, the x-axis is the demand, x, it's the number of items made. The vertical axis is the cost, C parentheses x, that's the cost of making that many items. Our initial number of items made is x subscript 0. Our increased number of items made is x subscript 0 plus 1. So our change in the number of items made is our delta x, it's the number 1. It's the spacing between those two coordinates on the x-axis. Now, the cost of making those items, the cost of making x subscript 0 items is here. The cost of making x subscript 0 plus 1 items is up here. So the change in cost is this interval on the vertical axis. I want to add a feature to this graph. I want to add a green right triangle as shown in this picture. Notice a couple of things about this green triangle. First of all, the hypotenuse of the triangle is part of a secant line for the function. One end of the hypotenuse is at this point on the graph, this red point. Those are the x and y coordinates of that point. The other end of the hypotenuse is at this point on the graph, that blue point. There's the x coordinate and there's the y coordinate. And the height of the triangle is the exact change in cost. Now consider this red triangle. Same graph, but in this red triangle, the hypotenuse of the triangle is part of a red tangent line. One end of the hypotenuse is at the point whose coordinates are x subscript 0, comma, C parentheses x subscript 0. So the x and y coordinates of this red point. But the other end of the hypotenuse is at this point on the tangent line that's not on the graph of the function. So we don't really have the coordinates of that point. The height of the triangle is unknown. We'll just call the height h. What would be the value of the height h? Well, to answer this, note that the height h is part of a right triangle. Let's draw that triangle here. The base of this triangle is delta x, which is the quantity 1, and the height is there. Also notice that the hypotenuse is part of the line that's tangent to the graph of the function at x equals x subscript 0. So that's this tangent line. The hypotenuse is part of that tangent line. That tangent line is tangent here. So that tangent line is going to have slope that's given by this expression, c prime parentheses x subscript 0. Remember, that's the derivative of c at x equals x subscript 0, and it's the slope of the tangent line. But remember that the slope in a right triangle, the slope of the hypotenuse is rise over run. So in our triangle, that slope m, which is c prime parentheses x subscript 0, that's our slope, and there's our rise over our run. So this simplifies to the equation that h equals c prime parentheses x subscript 0. Let's add that information to our drawing of the red triangle. So I've added that result about the value of h, and I've also shown the green triangle. Now notice that the green height, delta c, is not the same as the red height, h, but they're close. So we can think of, if the green quantity is the exact change in cost, we can think of the red quantity as the approximate change in cost. So to reiterate, the exact change in cost is that quantity delta c. It's shown up as the height on that green triangle, and it's computed by this formula. And the red height is the approximate change in cost, and it's given by that formula, c prime parentheses x subscript 0. Those two things are not the same. Those two quantities are not the same, but they're close. So the exact change, that green quantity, is roughly equal to the approximate change. Well, this idea generalizes to other functions, not just cost. So remember that the quantity c prime parentheses x 0 is called the marginal cost at a production level of x subscript 0. So we can generalize this to other quantities in the idea we would describe as using a marginal quantity to approximate a change in a quantity. So the exact change, that's that green quantity that we compute with a formula like this, is roughly equal to the approximate change, that's a red quantity that we compute using the marginal quantity. Let's do an example. Example 1 is similar to 2.7, number 33. But parts A, B, C are similar to problems 2.7, 4, 5, 6. These exact parts, A, B, C, were done in the video for homework 34. So in this example, we have a company manufacturing electric guitars, and the cost function for making a batch of X guitars is that function. So question A is, what's the cost of producing a batch of 50 guitars? So the result is that the cost of producing 50 guitars is this amount, $5,375. We computed that in the video for homework 34. Now question B, what's the cost of producing a batch of 51 guitars? We compute that by just substituting x equals 51 into the formula for C of x. So the result is that the cost of a batch of 51 guitars, the cost of manufacturing them, is this amount, $5449.75. Again, that result is from the video for homework 34. Question C is, if the batch size changes from a batch of 50 guitars to a larger batch of 51 guitars, what will be the change in cost of producing the batch? That is, what is delta C? Now we recognize that this is the exact value we're being asked for, so I'm going to do this solution in green. So our result is that the exact change in cost is $74.75. So again, all those three parts, A, B, C, were done in the video for homework 34. Let's go on though. Question D, if the batch size changes from x equals 50 to x equals 51, use the marginal cost function to find an approximate value for the change in cost. That is, use the marginal cost function to provide an approximation for delta C. In the book would call this using the marginal cost to approximate the cost of producing the 51st guitar. Well, let's go back up and review our strategy. The idea is we have computed this. This was that amount, $74.75. Now we're going to compute an approximation of that using the marginal cost. So I'm going to denote this in red. The approximate change in cost is C prime parentheses 50. So our strategy should be find C prime parentheses x and then substitute in x equals 50. So C prime parentheses x is the derivative. So we use our standard derivative rules. We'll start by using the sum and constant multiple rule. And then we'll use the constant function rule on this one and the power rule on these two. So our result is that C prime parentheses x is this expression, 100 minus 0.5x. That's the first part of our strategy, find C prime parentheses x. Now we have to finish. Our next part of the strategy is this, substitute in x equals 50 to get C prime parentheses 50. Now since we were labeling that as a red quantity, that approximate change, I'm going to do this calculation in red. So the result is that our approximate change is 75. Hey, look, that's very close to our exact change. The exact change was this green quantity, $74.75. The approximate change was this red quantity, $75. It's very close. And it might seem kind of strange to go through all this when you can just compute the exact change. But remember that in the previous video for homework 34, computing this C parentheses 51 was not terribly hard, but it was hard enough that it was deemed to be scrap paper work. And so in general, a lot of times using a formula to find a value can be a messy thing. And a lot of times computing a derivative results in a formula that's actually a simpler formula than the original function. Notice that the formula for C of x is a quadratic polynomial, degree 2. But the formula for C prime of x is a degree 1 polynomial. It's a simpler function to work with. So computing the approximate change was a very easy calculation that we could just do by hand, really simply. So using the marginal cost function often ends up being simpler than using the original cost function. And the thing is, the approximate change is so close to the exact change that it's very useful. And also you have to realize that, where would the exact change in cost come from? Well, the exact change in cost came from using this cost function. Where would a cost function like that come from? Well, if you're running the company that's making guitars, you have somebody whose job it is to figure out how much things cost. And a formula like this, the cost function, would already be a result of estimating things, approximating costs. So even though we called this quantity the exact change in cost, it's already got some approximations in it. So it's the exact change in the sense that we use this formula for the cost in an exact way, but that formula already had some approximations in it. So the idea that this result would be somehow better than this approximate result is not really true. They're both approximations in some sense. So the idea of approximating quantities by using marginal quantities is very attractive. All right, in the previous videos we discussed 4 terms having to do with business: demand, cost, revenue, and profit. And we discussed the idea of marginal quantities. Today we're going to introduce the idea of price. So price is represented by the small letter p, and it's a variable that represents the selling price per item. The price-demand equation is just what it sounds. It's an equation that relates the price, little p, and the demand, little x. So for example, this equation, 2x plus 3p equals 10. It could be a price-demand equation. Now in some situations, the price-demand equation can be solved for p in terms of x. So for example, if you solve that equation above for p, you end up with this. P equals minus 2/3 x plus 10/3. This equation has the letter p on one side and a bunch of stuff involving x on the other side. So it describes the price p as a function of the demand x. So we could use function notation to indicate that. We would write this: p parentheses x equals minus 2/3 times x plus 10/3. That doesn't mean p times x, it means p of x. And this is called the price function. Now let's revisit the idea of revenue. In previous videos, when you talked about revenue was just a given function that described how much money came in from selling a certain number of items. But now that we have the idea of selling price per item, we can revisit revenue, because how do you get money from selling items? Well, you get it by noting the number of items that were sold and multiplying that by the selling price per item. So in other words, demand times price. So x times p. Well, if p is a function of x, the revenue function would be x times p parentheses x. So that would be how we would build the revenue function. So for example, let's do our second example of the day. A company makes and sells hats. The price p and the demand x are related by this equation: x equals 1000 minus 20p. So question A is find p in terms of x. So in other words, solve this equation for p in terms of x. And we're also supposed to find the domain of the price function. There's a result of solving the equation for p in terms of x. We get p parentheses x equals minus 1 over 20 times x plus 50. Now let's think about this question. What's the domain of that function? Well, for that it helps to think about the graph of the function. Let's graph that function and think about it. Well, that seems like a pretty straightforward thing to do, but we should go slowly here. I want to first think about an abstract function, an abstract equation. So y equals minus 1 over 20 x plus 50. Looks like the same formula. Now that would be a straight line with slope m equals minus 1 over 20 and y-intercept at 0, 50. Now let's try to figure out this x-intercept. To find the x-intercept, we set y equal to 0 and solve for x. So the x-intercept is at 1000, 0. So the abstract equation, y equals minus 1 over 20 times x plus 50, has domain that's all real numbers. But what about the price function? That is an expression that's an equation, but we have to think about what the terms mean in that equation. In the price function, x is the number of items made. You cannot make a negative number of items. So for the price function, x cannot be less than 0. Also, you can't sell things for a negative price. You're not going to pay people to come and take away your items. So the selling price cannot be negative. We don't actually get to use that red part of the graph to the right of x equals 1000. So if I combine these two ideas, that x has to be greater than or equal to 0 and less than or equal to 1000, we get the domain for the price function. So that's our result. The domain of the price function is that interval. And in fact, we can graph the price function. Let's make a little graph here. So the price function graph is just that segment that has endpoints 0, 50 and 1000, 0. So the abstract equation, y equals minus 1 over 20 x plus 50, is this line that goes on forever in both directions. But when we think about the price function, it has the same formula, but it has a restricted domain. Question B. Find the revenue from the sale of x hats. And what's the domain of the revenue function? Well, to answer this, let's go back up and review what we know about revenue. Remember that revenue is x times p of x. It's the number of items sold times the selling price per item. So there's our resulting formula for the revenue function. It's this green circled thing. But now we have to answer this question. What's the domain of the revenue function? Well, that's actually not so hard to answer. Think about what went into building the revenue function. The revenue function was built by demand and price being multiplied together. Well, this formula for price is only valid for x greater than or equal to 0 and less than or equal to 1000. So that tells us that the resulting revenue formula is also only good for that interval. Let's go on. Question C. Find the marginal revenue at a production level of 400 hats and interpret the results. Well, remember what this means. That means we're supposed to find capital R prime parentheses 400. So the strategy should be find the derivative of the revenue function and then substitute in x equals 400. So let's do the derivative. So there I used the sum and constant multiple rule. Now we'll use the power rule. So the result is that r prime parentheses x is this formula, minus 1/10 x plus 50. Second part of this is to substitute in x equals 400 to get r prime parentheses 400. So there's our result. The marginal revenue at a production level of 400 hats is that quantity, 10. Now, the next part of this question says to interpret the results. That is, what we have circled here is a mathematical result, r prime parentheses 400 equals 10. To interpret those results means that we have to explain what they tell us about the selling of hats. Well, for that, let's go back up and review our results from earlier in the video. The idea is this, that we have computed one of these things, capital R prime parentheses 400, and it can be thought of as an approximation for this thing on the left, this exact change. That is the amount of revenue from selling 401 hats minus the amount of revenue from selling 400 hats. So interpreting means to just write in words. So there are a couple of ways of doing this. One would be the following. So one interpretation is that the revenue from selling a batch of 401 hats would be roughly $10 more than the revenue from selling 400 hats. We could also describe this in a different way. At a production level of 400 hats, revenue will increase at a rate roughly $10 per hat. So those are two different ways of describing in words what our mathematical result means about selling hats. Both of these kinds of interpretations are used in the book at different places. And in the MyLab problems, you'll find sometimes you have a multiple choice problem where you have to choose the correct interpretation. Sometimes you'll find ones that are written this way. Sometimes you'll find interpretations that are written that way. Let's go on to question D. Question D says, find the marginal revenue at a production level of 650 hats and interpret the results. So our result is that the marginal revenue at a production level of 650 hats is this number, negative 15. Now, what does that mean? That is, interpret those results. Well, if we think about this in the same way that we thought about the previous problem, think about these interpretations and write similar interpretations for the current problem, they would read as follows. The revenue from selling a batch of 651 hats would be roughly $15 less than the revenue from selling a batch of 650 hats. Now, how could that be? How could you sell more hats and actually have less revenue? Well, that's actually not crazy. Let's go back up and think about the price function. There. On this graph of the price function, to sell 650 hats would mean that you're looking on the price function graph at the place where x equals 650. This graph is telling you that you would have to have a price there. Now, to sell 651 hats, you would have to lower the price. You'd have to lower the price somewhat in order to sell 651 hats. So you're selling more hats, but you're selling them at a lower price. And according to our model, the lower price is enough lower that it cancels the benefit of the increased demand. Let's go back down to our interpretation. Let's write an interpretation the second way that we wrote in the previous problem. Something like this. At a production level of a certain number of hats, what's happening to the revenue? So there are two interpretations. The second one, at a production level of 650 hats, the revenue will decrease at a rate of roughly $15 per hat. So both of those are valid ways of interpreting the mathematical result that R prime parentheses 650 was this number minus 15. There's one more part to this question. Illustrate the results of C and D on the graph of R of x. Well, so this is the graph of R of x. Let's label it. There's our formula for R of x. Notice that it has two x-intercepts, 0, 0, and at 1000, 0. Notice that makes sense. When x equals 0, this horizontal axis is x, the number of items sold, and the vertical axis is revenue. When x is 0, that means you haven't sold any items. So revenue is the number of items sold times the selling price per item. If you haven't sold any items, then your revenue will be 0. Now, why does this point make sense? Why does it make sense that there would be an x-intercept on the revenue graph at 1000, 0? Well, let's go back up and look again at the price function. Remember, on the price function, the only way to sell 1000 items is for the price to be 0. You would have to give away the items to sell 1000 of them. So in other words, the revenue from selling 1000 items would be 0. So it makes sense that we would have an x-intercept at 1000, 0. Now, what about our results of C and D? In question C, we found that R prime parentheses 400 equals 10. Well, that is going to be the slope of a tangent line. The line that's tangent to the graph of the function at 400. And the result in question D was R prime parentheses 650 was minus 15. Well, that's the slope of a tangent line as well. The tangent line at the point on the graph where x is 650. All right, well, that's the end of that example, and that's the end of the video. Thank you.